scientific death.
Think about walking into an indoor swimming pool. You take a deep breath, and that sharp, clean scent instantly hits you. We are entirely conditioned to accept this as the smell of chlorine, hard at work keeping the water sanitized. But pure chlorine doesn't actually smell like that. The scent you are noticing belongs to a completely different chemical, a highly irritating, light-sensitive, and violently explosive compound known as nitrogen trichloride. Facility managers do not pour this into the water on purpose. It is an accidental byproduct of the disinfection process, and it has been stinging the eyes and lungs of swimmers for decades. That comforting, nostalgic scent of a clean public pool is actually the chemical signature of a volatile, energy-packed molecule that is quite literally ready to snap. The recipe for this compound requires two main ingredients. First, the pool facility pumps in standard chemical disinfectants, which dissolve to form hypochloric acid. The second ingredient comes directly from the swimmers. When people jump into the water, they introduce nitrogen-heavy organic compounds, mostly urea from sweat, and inevitably urine. When the hypochlorous acid meets that nitrogen, a stepwise chemical reaction kicks off. The acid attacks the nitrogen compounds, stripping away hydrogen atoms and replacing them with chlorine. It forms monochloramine, then dichloramine, and finally nitrogen trichloride. This end product is highly endothermic. Its formation packs a massive amount of energy, positive 232 kilojoules per mole, straight into its chemical bonds. Human biology and commercial cleaners mix to inadvertently manufacture a shock-sensitive hazard. To understand why it is so prone to violent decomposition, we have to look closely at its atomic blueprint. Let's build the molecule. It starts with a single nitrogen atom in the center, sharing single covalent bonds with 3 surrounding chlorine atoms. If we count up all the valence electrons holding this together, we get exactly 26. After satisfying the central bonds and filling out the outer shells of the chlorine atoms, 2 electrons are left over. They sit right on top of the central nitrogen atom as a non-bonding lone pair. That lone pair takes up physical space. Its negative charge pushes down hard on the 3 chlorine atoms, forcing the entire structure to bend out of a flat plane and into a distinct 3-dimensional shape called a trigonal pyramid. Because of that downward pressure, the space between the chlorine atoms is squeezed tight, compressed to exactly 107.1 degrees. That specific, tightly packed geometry creates an intense amount of invisible subatomic tension. To see why that tension is dangerous, compare it to a familiar household cousin, standard ammonia. Ammonia shares the exact same trigonal pyramidal geometry, but it is highly stable. The stability comes down to how the atoms share electrons, a property called electronegativity. In ammonia, the nitrogen pulls electrons away from its small hydrogen atoms. The polarities of the bonds and that top lone pair all point in the same upward direction, creating a strong, stable dipole moment of 1.47 dBi. Nitrogen trichloride operates in reverse. Chlorine is more electronegative than nitrogen, so it pulls the electron density down and away from the center. This downward pull actively fights the upward pull of the lone pair, canceling out the molecule's dipole moment to a weak 0.6 dBi. Those 3 chlorine atoms are physically massive. Crammed together at that tight 107-degree angle, their large electron clouds violently repel each other. This intense crowding is called steric strain, and it makes the central nitrogen-chlorine bonds incredibly weak. Simply swapping 3 small hydrogen atoms for 3 large chlorine atoms transforms a stable compound into a molecule that is literally tearing itself apart. That structural repulsion is exactly what makes it so sensitive to light, heat, and mechanical shock. That microscopic strain translates directly into macroscopic violence. In 1812, French chemist Pierre Louis Dulong synthesized nitrogen trichloride for the first time by mixing ammonium chloride with chlorine gas. The yellow oil proved instantly volatile, detonating with enough force to permanently cause Dulong an eye and 2 of his fingers. Despite the clear danger, other researchers pushed forward. The compound's inherent instability soon caused separate laboratory explosions that injured both Humphry Davy and Michael Faraday. The invisible repulsion between 3 chlorine atoms produced unpredictable shockwaves that blinded some of the greatest minds in scientific history. A beat of disbelief. Yet, knowing its explosive and toxic profile, early 20th century industries actually manufactured the gas on purpose. Under the trademark Agene, they used nitrogen trichloride as a bleaching agent to whiten baking flour. For decades, it was mixed directly into the commercial food supply. The practice was finally abruptly banned in the United States in 1949, but only after animal testing revealed severe toxicological effects. Today, we no longer put it in our food. Instead, water treatment plants and aquatic facilities spend millions of dollars on ventilation and UV photolysis systems, trying to mitigate its accidental formation. Nitrogen trichloride proves that atomic geometry is destiny. A slight shift in electron pull and a compressed bond angle are the only differences between a safe household cleaner and a volatile explosive, lingering right under our noses.